pertaining to coral reefs, but I want to look at the coral, how the coral actually takes minerals out of the water, and specifically what kinds of things affect that process of removing minerals from the water in order to produce the reefs, which are composed principally of calcium carbonate. There are some reefs that have magnesium in them as well, and depending on how much magnesium is actually replaces the calcium, it can grade all the way from maybe a few percent up to something where there are equal molar quantities of both calcium and magnesium in the mineral itself. And when that happens, you no longer have the usual kinds of composition that you get for reefs. You actually can get a reef that contains a lot of the mineral called dolomite, which is actually a calcium magnesium carbonate. But calcium carbonate itself exists in two forms, and one of them is called calcite, which is a fairly familiar mineral, and there's another one called aragonite. And I have samples of calcite. These are not from the sea, but I just wanted to show you the difference in crystal structure between calcite and aragonite. Now, calcite is actually probably the more thermodynamically stable of the two. That means that at very, very high temperatures, aragonite would actually convert to calcite. But you do get a lot of aragonite forming under certain sets of environmental conditions. And most of the reefs that we see are actually aragonite-based reefs. But we do have calcite-based reefs as well. This is a specimen of calcite, and the crystal structure of this pretty large specimen of calcite. The crystal structure of this is something that's called scalenohedral. Basically, you've got all the sides of this, and you can see where the light is reflecting off of this, kind of form scalene triangles. So you've got triangles where none of the sides, let's see if I can get the light on this one, none of the sides are equal on these things. But there's a number of these scalene types of surface, and this is one kind of calcite that one finds naturally. But this is, as I say, is not from the sea. I wanted to show you some aragonite as well. And aragonite crystallizes out in a different crystal system. So calcite itself actually is in the trigonal rhombohedral crystal system. And what we have with aragonite is orthorhombic crystals. Now, these crystals are actually crystals that where all the sides are perpendicular to one another, but the sides, each of the three dimensions is of a different length. That's what makes a rhombohedron. So this is a rhombohedral specimen, a smaller specimen of aragonite, but this is typical of a kind of aragonite. This particular material comes from Spain, and this kind of aragonite, the crystals actually intergrow with one another, and they form a kind of almost hexagonal shape. I don't know if you can see that. Maybe if I get this a little bit closer to the camera, you might be able to see sort of a pseudo hexagon, if you can barely make out that shape there on the edge. And then there are other kinds of aragonite that form masses. This is another specimen of aragonite. May look a little bit yellow when you see it, but it's actually quite white, beautifully white. Most of these minerals are highly fluorescent, that is under ultraviolet light. This particular one will glow with a brilliant green glow, and many of the calcites glow with a red glow. But this is the kind of material that is actually present in most reefs. But again, this is not of biological origin. This is something that was actually mined. But I just wanted to show you because I didn't actually have a coral skeleton that I could lay my hands on. I'm sure I have one around somewhere. I just couldn't find it real fast. So anyway, coral polyps themselves are small. They're maybe only a few millimeters in diameter. They've got an outer epithelial layer, and they've got an inner jelly-like tissue that's called the mesoglia, M-E-S-O-G-L-E-A, and they actually attach themselves to the substrate through a tissue that is called the basal plate. Another name for the basal plate, it's also called the calicle, C-A-L-I-C-L-E, and it actually forms a calcareous ring. And when we talk about something that's calcareous, what we're referring to is that it's calcium carbonate laid down ring, and this is an annular ring. It's a ring that that will grow, and it also grows vertically. And when it gets to a particular height, sometimes it will actually septate. That is, it'll start to spread out, and there'll be a septum that's dividing the two pieces, and sometimes a new basal plate will form at a higher level. And this is the way that coral colonies actually build up coral reefs. So we have, for instance, if we actually look at the deposition of how fast coral actually deposits itself, coral itself will actually sequester calcium ions and carbonate ions from the seawater, and per square meter of polyp, you actually get a deposition rate of about 10 grams of calcium carbonate per day. So you can imagine over an entire coral reef, the amount of accretion, that is the amount of coral growth, is can be quite high over a period of time. However, we have things that are also working against the coral growth. There are organisms that attack the coral. There are fish that eat coral. There are adverse environmental conditions that will destroy the coral. Some corals are really quite fragile, and when you have a lot of very violent wave activity, masses of coral will actually break off, and that can cause the loss of a lot of the reef when that happens. So you not only have things like fish eating corals, but there are other creatures as well that will attack corals. There are things that will bore into corals and will actually weaken the coral structure. There was an El Nino that occurred in 1982, between 1982 and 1983, and this was, I've got a paper here that actually talks about a particular coral reef system that's on the Uva Island in Panama. And according to this paper, the amount of coral that's actually been lost to erosion after that event, after the El Nino that occurred in 82 and 83, the reef is now diminishing at the rate of 4.8 times 10 to the third, so that would be 4,800 kilograms per year. That's it's not. I mean, for an entire reef, that may not seem like an enormous amount, but that's still 4,800 kilograms. We're still talking about a few metric tons of material, almost 5 metric tons of material that's actually being taken off of this reef. And this is just one particular reef, but other reefs are also being affected and having there are environmental impacts to other reefs as well. Coral deposition is also affected not only by the concentrations of things like calcium in the water, but it's also affected by the amount of sunlight that is actually falling on the reef, because although you do get a certain amount of calcium carbonate deposition even in the dark, many of the coral building organisms actually have a symbiotic relationship with zooxanthellae. These are the algae that actually live within the tissues of these creatures, and the zooxanthellae are actually involved in photosynthesis, and it turns out that the photosynthetic rate of these organisms is actually to a large extent matched by the coral deposition rate, or I should say that the coral deposition rate is matched by the photosynthetic rate. So the more photosynthesis that you have, it seems that the more coral deposition that you get, because the coral itself, the organism, actually requires energy in order to deposit the coral exoskeleton, and it's getting that energy basically from the zooxanthellae, these photosynthetic algae in its tissues. So that's very important as well.